Sudah di Zoom. Dari baik.
Ladies and gentlemen, we will begin our webinar shortly. Please make sure your microphone is on mute and you are in your most comfortable position. Thank you.
Saya keluar.
Nggak di sini suara ini.
Nanti mantul Bu, masuk Tsunami.
Present with us in Zoom, the Honorable Deputy of Geophysics of BMKG, Dr. Nelly Floridariama, SSC MSI.
Selamat pagi, Bapak Ibu.
Selamat pagi, Ibu. Mohon izin, Ibu, apakah sudah bisa kami mulai?
Silakan.
Assalamualaikum warahmatullahi wabarakatuh. Salam, Om Swastiastu, Namo Buddhaya. Excellency Deputy Head for Geophysics of BMKG, Dr. Nelly Floridariama, SSC MSI, the Honorable Director of Earthquake and Tsunami, Dr. Daryono, SSC MSI, Professor Soichi Yoshioka from Kobe University, all Head of Regional Office BMKG, all Head of Work Team and Responsible Person in the Directorate of Earthquake and Tsunami, all speakers and webinar participants. Good morning, ladies and gentlemen. First of all, let us give thanks to God Almighty. For His grace, we can gather this morning in the webinar Preparedness for Megathrust Earthquake, Sources, Impacts, and Mitigation. This morning is a special webinar because this morning we have a professor from Kobe University, Japan, Professor Soichi Yoshioka. Welcome to the BMKG headquarters, Prof. It is truly an honor to have you with us, and we appreciate your time and presence in this event. Ladies and gentlemen, let me introduce myself. My name is Shafira, and I will be your Master of Ceremony for this event. On behalf of the organizing committee, I would like to welcome all of you, both those attending online and offline in this webinar. It is a great honor to have all of you join us in this important discussion on earthquake preparedness and disaster mitigation. On this occasion, allow us to guide you through this event. Before we begin, please allow us to read out the agenda for this morning. First, singing BMKG March. Second, opening remarks by Deputy Head of Geophysics for BMKG. Third, photo session. Fourth, expert presentation and Q&A session. And last but not least, closing remarks by Director of Earthquake and Tsunami. Okay, Let's start to the first agenda, singing BMKG March. Ladies and gentlemen, please stand. May you please be seated. Thank you. Ladies and gentlemen, the next agenda is opening remarks by Deputy Head of Geophysics for BMKG to Dr. Nelly Floridariama, SSI MSI. Time is yours.
Terima kasih Mbak Samira. The Honorable Professor Soichi Yoshioka from Kobe University. Welcome to Jakarta and welcome to Indonesia. As I know, this is your first time to visit Indonesia, and I hope you will enjoy Indonesia. Director of Earthquake and Tsunami, Dr. Daryono. Director of Engineering Seismology, Potential Geophysics and Science of Times, Bapak Setio Aji Prayudi. Head of STMKG, Dr. Denny Septiadi. All heads of work teams and responsible person in the Director of Earthquake and Tsunami, speakers and webinar participants. Assalamualaikum warahmatullahi wabarakatuh. Shalom, Om Swastiastu, Namo Buddhaya, and greeting of peace for all of us. First of all, let us give praise and gratitude to the presence of God Almighty, who has given His blessings and grace so that on this blessing day, we are still given the opportunity and health together for this webinar, Preparedness for Megathrust Earthquake Sources, Impacts, and Mitigation. Ladies and gentlemen, as we know, Indonesia is located above 4 active tectonic plates in the world, namely the Indo-Australian plate, Eurasian plate, Pacific plate, and Philippine plate. This geological condition causes our region to be one of the areas of the highest seismic activity in the world. Several times in history, Indonesia has experienced major earthquakes that have caused significant impacts both in terms of casualties and infrastructure damage. One of the biggest threats we face is megathrust earthquakes, which are large earthquakes that originate from subduction zones along the meeting of tectonic plates. This type of earthquake not only has the potential to cause severe shaking, but also triggers tsunami that can have widespread impacts in coastal areas. Therefore, understanding the sources, characteristics, and mitigation of megathrust earthquakes is our shared responsibility. Ladies and gentlemen, this webinar is very important because it provides an opportunity for all of us to explore further the potential threat of a megatrust, how its mechanism occurs, and the mitigation steps we can take. Through discussion involving experts in the field of geophysics, disaster and disaster mitigation, we hope to gain new insights that can be applied in disaster preparedness and risk reduction efforts. We need to understand that disaster preparedness is not only about physical readiness and infrastructure, but also readiness in terms of knowledge, education, and good coordination between stakeholders. Ladies and gentlemen, we hope that the discussion in this webinar will not only provide insights, but also serve as a spark to formulate more effective mitigation strategies. Measures such as public education, earthquake-resistant infrastructure development, accurate early warning, and well-thought-out evacuation plans must continue to be improved so that we can reduce the impact of disasters that may occur. Finally, I would like to thank all the speakers, organizers, and participants who have participated in this activity, and may this webinar bring a great benefits and further strengthen our preparedness in facing the threat of a megathrust earthquake. I hereby declare the webinar preparedness of megathrust earthquake, sources, impact, and mitigation is officially open. Congratulations on participating in the event. Hopefully it will be successful. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you, Dr. Nelly Floridariama, SSC MSE, for your remarks and for officially opening this morning webinar. Ladies and gentlemen, the next agenda is photo session. We would like to take a group photo to capture this special moment together. So we kindly ask everyone to turn on their cameras and get ready for the photo session. We will wait for a few moments to allow everyone to turn on their cameras, and let's make sure we are all visible on the screen. And if you are comfortable, please smile for the camera. Our technical team will take multiple screenshots to ensure we get the best shoot. So please stay in position and smile.
Is
All right. There is 7 page. Page 1. Page 2. Page 3. Page 4. Next, page 5. Next, page 6. Okay, page 7. And the last, page 8. Thank you, everyone. We truly appreciate your participation. Now let's continue with our agenda. Ladies and gentlemen, we will enter to the main agenda, expert presentation and Q&A session, which will be guided by our moderator, Mr. Sidik Hargo Pandadaran, MDM. To Mr. Sidik, time is yours.
Okay. Sorry for the noise. So thank you, Miss Shafira, for the time. So today I'm the moderator for the next sessions. And in this session, we have four expert speaker, three from BMKG and one from Kobe University, Japan. But before we start our sessions, their presentations, I want to introduce some rules for the webinars. The Q&A sessions will be opened after the end of their presentations. And then the second, first, 3 questions will be offered to the offline participants. So the first opportunity will be given to the offline participants and then followed by the online participants. For the online participants, you can directly ask to the speakers by opening your microphone or by typing your questions in the Zoom chat box. So in the Zoom chat box, you can use this format from your name to speaker's name and your questions. And you can also use Indonesian language in your questions. Okay, now we move to the first speakers. Next, please. Okay. The first speaker is Dr. Wijayanto. He is the head of the Earthquake Information and Tsunami Early Warning Operational Team. He graduated from Gajah Mada University for his doctoral degree, and he had some work experiences. With the latest experience was head of the Earthquake Information and Tsunami Early Warning Operational Team. And he has some publications. The latest publication is Spatial Distribution of PS30 based on MASW and HPSR inversion in Gunung Kidul, Yogyakarta. And maybe for our information, if you received any information about earthquake and tsunami warning, maybe, yeah, all of those informations are supervised by Dr. Wijayanto. Okay, I would like to invite Dr. Wijayanto. Dr. Wijayanto, can you share your screen, please?
Okay, thank you, Mas Sidik.
Okay.
Do you hear my voice?
Yeah, I can hear you. So, okay, I will inform the detailed agenda. You have 10 minutes for your presentation time, and I will remind you 2 minutes, 1 minute, and when your time is up. It's okay?
Okay.
Okay, you can start your presentations by now, please.
Okay, could you see my
Yes.
presentation?
Yes, I can see it.
Okay, thank you, Chairman. First of all, I would like to say thank you for the organizing committee, and then Your Excellency, Deputy of Geophysics, Dr. Nelly Florida, Director for Earthquake and Tsunami, Dr. Daryono, Professor Yasioka from Kobe University, and then all of participants from this webinar. Assalamualaikum warahmatullahi wabarakatuh. Good morning. Today I will present the current status of Indonesia Tsunami Warning System, or INATIUS, that already established starting from 2008, and then this is the current status up to 2024. My presentation will be introduction, monitoring system, processing system, dissemination system, and then the global rule of Inatus and others. First, this is the condition of Indonesia as we see from the picture that our country, Indonesia, is located in the earthquake-prone area. This is located in the 13 megathrust along west of Aceh, west of Sumatra, south of Java. There is 30 megathrust. Also, there is many active fault. Is more than the 300 active fault because this is because Indonesia located in the Indo-Australian plate tectonic and then Eurasia, Pacific, and Philippines. We can see here that our country, Indonesia, is very active. We can see that the seismicity in Indonesia during 1963 to 2023 is very active. Also, Indonesia also located in the tsunami-prone area. We can see here that more than 46% of coastline in Indonesia is prone of tsunami. This is our tsunami warning system that our Inatus is established or inaugurated on November 11, 2008 by our President Susilo Bambang Yudhoyono. In that time that our system produce the earthquake information and tsunami warning and disseminate within 5 minutes. But currently, starting from 2023, we already disseminate the earthquake information and tsunami warning within 3 minutes. This is faster than the first step. So we already inform the earthquake information and tsunami warning within 3 minutes. So the next is what the monitoring system. So mainly we divide into part that the part one is culture and structure. For the component structure, there are 3 components, yeah, one monitoring system, processing system, and dissemination system. For the monitoring system operated by BMKG, we install many instruments to monitor the earthquake phenomena, such as the seismometer and then the accelerometer. Also, we collaborate with another institution to monitor the tsunami observation level with the PAG and then also BRIN to install the tsunami kit, TED kit, and then the buoy. So all of this data is coming to our center. We process the data, will be processed by earthquake processing and tsunami processing, will be produce some output, call it the earthquake information and tsunami warning. So this earthquake information and tsunami warning will be disseminated to multi-mode dissemination. Currently, we disseminate through the stakeholder or also directly to coastline community. Our stakeholder is many stakeholders such as BNPB, BPBD, Kominfo, and then mass media, and then police, and etc. This is our seismic monitoring system. Currently, we already have around 553 seismometer installed all of Indonesian region. This is our existing is from the Aceh to Papua. There is many seismometer. From this condition, we are sure that we can inform the earthquake information and tsunami warning within 3 minutes for the first information. Also, except for Indonesia, we also collaborated with international country to monitor the earthquake because Indonesia not just responsible for national, we also responsible for Indian Ocean and ASEAN. So this is the picture that we also collaborate or data sharing with another country. And this is the sea level monitoring network that we, as I said before, that we collaborate with another institution such as BMKG and BRIN. We are Ministry of Fishery. Currently, for this TED kits, we have 266 sensor. Also, for this year, we already finished to install the Tsunami kit in around Indonesia region is around 100 Tsunami kits. So in totally, now we already have around 363 Tsunami kit sensor. So for the processing system, mainly we have the main system in Jakarta. We also have the backup system in Bali, and then we have in Jakarta we have the training system in Jakarta. Also we have a regional earthquake processing system. It's around 10 regional seismic system in Indonesia. Also we have some seismic station or UPT in Indonesia. We have around 33 geophysical station. So mainly in our processing system, we divide into part. So for the earthquake analysis, we using Seiscompi. The Seiscompi will produce the earthquake information such as origin time, magnitude, depth, location, and etc. Also for the tsunami processing, we use those tsunami observation and simulation system. Basically, this TOS is using two system that will compute the tsunami proposal using the pre-calculated tsunami database, and then also we use the scenario using the real-time or on-fly scenario. So this TOS will produce the tsunami warning. Mainly, we inform the estimated tsunami height and estimated time arrival of the tsunami. This is our pre-calculated database. Currently, we have around 24,000 scenarios along the Indonesia. This scenario is we calculated around the subduction zone or the Megathrust area. Also in Sunda Strait, also in Molucca, in north of Papua, and then in Sulawesi. So this pre-calculated scenario, we produce the time arrival of tsunami and then also the estimated height of the tsunami. This is our capacity in our center in Jakarta. So this is our operational room. So we monitor the earthquake using Seiscompi. Also, if there is some tsunami proposal, we will analyze using TOS, and then we have the dissemination system. Also, all of the data will be validated using the INATNT, or this INATNT is system to monitor the sea level data, and then also if all of our data will be reanalysis or will be quality control before we save in our database. So this is our backup system in Bali. So except in Jakarta, if there is some problem in Jakarta, we will offer our system in Bali. This is our backup system in Bali. Next is for the dissemination system. So we use the multimodal dissemination system to disseminate our earthquake information and tsunami warning. Currently, we have many modes of communication using SMS, fax, email, and then we have website. And then for warning receiver system for the new generation, we already installed in 500 location along the BPPD and then the local government. Also, we have mass media such as Facebook, Twitter, and then Telegram, also Instagram. We have also we install the smartphone application for mobile information, mobile phone. Also, currently also we have the radio
Sorry.
broadcast. If there is some problem about the communication, we already have the radio broadcast using the communication. So this is our
Sorry, Dr. Wijayanto, your time is 2 minutes more. Okay.
okay. So this is our summary warning timeline. So we are currently usually we have 4 warning, yeah, bulletin 1, bulletin 2, and bulletin 3, and bulletin 4. Bulletin 1 is for earthquake parameter, bulletin 2 is for the earthquake parameter update, and then bulletin 3 is for the tactical observation, and then bulletin 4 is for the ending of the tsunami warning. And then for the global rule of Ignatius, so currently BMKG not just provide the information for national level, but also we have mandatory to inform our warning to Indian Ocean. So BMKG also BMKG or Indonesia as the tsunami service provider to inform the tsunami around the Indian Ocean country. Also, we are also in the IEC or ASEAN Earthquake Information Center for Southeast ASEAN country. So, and then the other for our challenge, there is still many challenge to improve our system. So we need to speed up our calculation to provide the rapid earthquake information and tsunami warning. So we also have to some problem about the non-seismic tsunami, such as the Krakatau tsunami or the tsunami from Lancet. So this is still our problem also about the data information accuracy. Sometimes the accuracy of our information of warning is still not so good accuracy. Also, our data quality of our monitoring system is still some noisy seismic station. So from that challenge or problem, so we still need to enhance our capacity to operate the Inatus to issue the earthquake information and tsunami warning. Also, we need to develop or to improve our system to generate by specific cause, such as for volcanic or landslide. Also, the improvement of the data quality is very important also for us. That's all my presentation. Thank you, Mr. Siddiq. Time is yours.
Okay, thank you, Dr. Wijayanto, for your presentations. So, okay, we have some time to listen to Indonesian songs first. Wait a moment. Okay, thank you for the time. So I've controlled some information from Dr. Wijayanto presentations. So we have 3 points. The first is BMKG has many roles, not only in national scope, but also international scope to disseminate tsunami informations. And then the second one is BMKG has a lot of instruments to support faster dissemination information. And now BMKG capable to disseminate earthquake and tsunami information within 3 minutes. And the last, BMKG still has some challenges such as data quality and tsunami early warnings, especially from non-seismic sources. Okay, I got a request from the team that the information must be
Yeah.
all the information must be okay. So I have some requests from our team that the information must be delivered in Indonesian language. So I will deliver in Indonesian for the conclusions. Jadi BMKG mempunyai beberapa role Bapak Ibu. Jadi role yang pertama yaitu mendesiminasikan informasi gempa bumi dan tsunami di internal Indonesia atau national scope. Lalu yang kedua mendiseminasikan informasi tersebut juga ke negara-negara lain, terutama di Samudra Hindia dan Pasifik juga seperti itu. Lalu yang kedua, BMKG punya banyak instrumen dan makin ke sini semakin bertambah, dan untuk waktu diseminasinya itu untuk diseminasi gempa bumi dan tsunami dapat dilakukan dalam waktu yang lebih 3 menit seperti itu. Lalu yang terakhir, BMKG juga masih memiliki beberapa tantangan ke depannya, seperti halnya kualitas data dan yang paling penting yaitu tsunami akibat faktor non-seismik seperti itu. Oke, thank you Dr. Wijayanto for your presentations. So let's move to the second presenter. Okay. The second presenter is Dr. Weniza. She is head of the Earthquake and Tsunami Mitigation team. She graduated for her doctoral program at Institute of Technology Bandung in Geophysical Engineering. She had a lot of experience for working, and the latest her experience is head of the Earthquake and Tsunami Mitigation team, and she also has role in international scope, such as chair working group 1 in ICG IoT WMS in UNESCO. Okay, let me introduce her publication also. The latest her publication is Rapid Tsunami Inundation Forecast using pre-computed earthquake scenarios and offshore data. That was her dissertation thesis. Okay. I would like to invite Dr. Weniza. Dr. Weniza, can you hear me?
Yes.
Okay, you can share your screen. Okay, I can share your screen. You have 10 minutes for your presentation time. And please.
Okay, Bismillahirrahmanirrahim. Good afternoon. In the eastern part, and good morning. We are in the western. Thank you very much for giving me an opportunity to present about the earthquake and tsunami mitigation. Here is the outline that I would like to mention and share today. It's about the flow chart of the Inatus that already mentioned by Dr. Wijayanto, and also mentioned about the gap between technology and user capacity, and several program activity that has been conducted under the mitigation program of BMKG. It's already mentioned by Dr. Wijayanto. It's related with the flowchart of the Indonesia tsunami warning system. Is mostly there are 2 components under the Inatus flow. First is the structure of called upstream. The second one is the culture or downstream. For the structure or the upstream part is mostly about the technology coming from the monitoring system, processing system, and dissemination system. Then going to the culture or downstream is about the A stakeholder will receive the information of the earthquake and tsunami warning coming from the upstream, and the community in the risk as the last target for the information. This has become something very challenging related with the information going to the community. So from that flow, we can see the gap between the technology innovation and the user capacity. In the technology part, mostly about the observation and modeling data information, then going to the user, it's become the challenge related with the understanding, skill, awareness, and response of the user to understand about the data and information, the skill and awareness, how do they do and react about the data and that information, and how they respond that information to be timely manner. So this is the first gap of the user related with the understandings and response. The second gap is about the involvement of the business or private sector, where this is the strategic sector that would need involved to need to involve on this flow. But again, it's still on part of the gap on the technology and user capacity. And the last gap is about the sustainability of the user capacity to respond and to understand all the knowledge they have. This is the technology that I already mentioned. We have a seismograph, we have a processing system, and also we have dissemination system that we have now for 500 for the dissemination of the warning receiver system. Is about the technology. So from this technology, actually, there are we need to have some program or activity in order to fulfill the gap of that between technology and the user. Here is one of the programs under BMKG program. First program is Tsunami Hazard Map. Actually, this is a program is in coordination with the local government in order to identify tsunami hazard potential. Currently, we have 261 tsunami hazard map level province, regency, city, village in 23 provinces. In this map is actually talk about the estimation potential of tsunami Indonesian height and also the estimation of the arrival time. And from all these maps, there are 230 maps in Indonesia Megathrust zone. So it is a large number of the map, of course, in area of the Megathrust zone. The second program is under BMKG program is ISO 22328-3. The name of this ISO is the guideline for the implementation of a community-based early warning system for tsunami. The target of this ISO is actually for the public-private based on this instrument as the their business as such. The business is such as industry, tourism, and other critical business in order to accelerate the achievement of the successful early warning, early action. And also, this is become the benefit to the business and the private sector when they are applying the ISO for better market exposure. This is actually the initiative coming from Indonesia and BMKG as the conceptor of this ISO. This is the timeline how we struggle with the ISO. With this started from 2018 as the initiative or any proposal in the Sydney meetings. And also then we have acceptance from the ISO member state to continue our new work item proposal under the ISO body. Then all the process that we go to that all timeline, then 2022, the ISO has already published as the international standard. The next program is Earthquake Fuel School. This program is as the national priority programs This earthquake field school, called together with the BMKG Goes to School or BGTS, are the national priority programs at the educating communities and particularly in earthquake and tsunami mitigation. Currently, there are more than 178 locations that has been implemented earthquake field school, which is across 132 regency city and 24 provinces throughout Indonesia. And also for the BMKG Goes to School has been carried out in 772 schools across to 94 regency city in 24 provinces throughout Indonesia. So this is become the national priority program that spread out all the Indonesian province. This is the scope of the activity under the earthquake field school activity. Actually, it's about the pre-test and post-test. It's about the tabletop exercise, and also this earthquake field school has a recommendation to follow up by the stakeholder to do their next step on as their rules. And this is all the stakeholder that who involved on this program is like NDMO, is like also the community, like village district head, school, military, and tourism manager, industrial or critical infrastructure institution, and relevant agency and media. And about the BMKG Goes to School is actually focused for the school coming from the elementary school, junior high school, and high school, senior high school, where it is carried out by BMKG with the teacher who are participant in the earthquake and tsunami field school. There are some activity for this BMKG to school, such as the presentation, of course, mention about the potential of the earthquake and tsunami around their location, around in their area. And also, it's about simulation and also produce the SOP for the earthquake and tsunami response. And also, there is also simulation to test a school evacuation plan. It's also related with this program. Now we have we already implemented Tsunami Ready program. Is actually this program under UNESCO IOC program. With the aim of this program is in order to build the resilient communities through the awareness and preparedness strategies, protecting life, livelihood, and protecting from tsunami in Paris, especially in Indonesia, Indian Ocean countries. Currently in Indonesia, already implemented for 22 communities around the Indonesian region, and it will be more at more these communities that encourage to implement this already. The community that have recognition from the UNESCO, they actually already fulfilled 12 indicators that mentioned on these programs. This program coming from the assessment, preparedness, and response. And from all the programs, we have the success story of the BMKG earthquake field school. First success story is occurred in Palu earthquake tsunami. Palu earthquake tsunami occurred in 2018. But we have this program in 2015, and one of the participants from this program informed that they are safe from this earthquake and tsunami Palu. These participants coming from the media, then what he mentioned and what he did during the earthquake, we will see on next video. The second success story is coming from the 2021 Mamuju earthquakes. Here is the Bapak Jaharudin. Mr. Jaharudin is coming from, he is head of district of Mamuju. He also one of the supervisor that Mamuju earthquake occurred in 2021, and the program of the earthquake conducted in 2019. So it's mean 2 years after the earthquake field school, the earthquake occurred, and the survivor of this mentioned their their safety from this earthquake. So this is the video from all of them. I hope can you hear this video? Okay, this video will talk about the importance of the earthquake feels full, and also what has been done by the supervisor during the earthquake.
Kalau di SLG ya, SLG memang ya salah satu pembelajaran kami secara internal bagi saya pribadi, ya kan, itu merasa bangga. Hadirnya SLG itu kami bisa menambah wawasan itu. Saya tidak bisa apa-apa Pak di masyarakat tanpa SLG juga. Itu tenis kemarin cukup bagus itu dari SLG kemarin kami sampai akhirnya itu. Ya saya bisa itu karena itu lah. Trik-trik yang kita berikan sampai akhir itu, trik itu ya saya bangga untuk. Saya kan orang komunikasi, jadi saya yang paling banyak bersuara mungkin saat ini. Iya, aktif. Gitu. Saya aktif Bu, memang saya aktif di luar. Kenapa saya rajin bertanya? Karena saya harus tahu. Saya harus sampaikan ke masyarakat, nggak buta-buta kan. Saya harus jelas, ya kan, terperinci. Saya bisa jelaskan begini tujuannya.
Okay, this is the first video from the Pak Rudin. He mentioned about he knows about the trip and trick what during the earthquake occurred, and he is actually very active during the earthquake school. And with his knowledge, he can share their knowledge to other. And this is the second supervisor coming from the Mamuju earthquake. Is head of district of Mamuju. Okay.
Kebetulan sebelum gempa bumi itu saya pernah ikut sekolah lapangan SLG. Jadi ya karena ada semacam alarm gempa kecil waktu siang, jadi saya sudah kasih tahu saya punya istri dengan anak bahwa kita siap. Kebetulan di rumah kan ada meja makan saya terbuat dari kayu, agak tebal juga, bukan dari kaca. Jadi saya antisipasinya meja makan itu saya sorong semua kursinya, nanti kalau ada kejadian kita berlindung di bawah meja lah. Begitu. Sangat-sangat bermanfaat karena yang pertama itu ya kami terlindungi dulu kepala kan. Akhirnya saya bertiga sama istri sama anak ya berlindung di bawah meja dulu sampai betul-betul sudah rame di luar, baru kami keluar. Jadi tolong kepada generasi muda atau yang sempat dapat sekolah SLG, tolong serius untuk mengikuti mata pelajaran yang ada selama kita mengikuti proses belajar itu.
Okay, it is the same thing from the Jarudin mentioned about he knows what he should do during the earthquake, and also he encouraged the young people to be active and to have need to have a knowledge about earthquake. Then I think the last slide is actually the education book that we have been published. Most of you can download this book. This book is about the catalog of the structured earthquake, Indonesian tsunami catalog, and others is about also the earthquake and tsunami safety guideline for people with disabilities, and the last one is earthquake deformation. I think it's all from my side. Again, back to the moderator. Thank you very much for your attention.
Okay, thank you very much, Dr. Wenizia, for your time. So I think we have learned many things about how BMKG disseminate their information about earthquake and tsunami. So I have summarized some information from her presentations. The first one is BMKG has many instruments to disseminate earthquake and tsunami information, such as WRSNG, tsunami sirens, info, BMKG application, and so on. And for the fun fact, info BMKG is the most highest downloaded applications among Indonesian agency institution. So it is downloaded more than 5 million times. It means that BMKG applications is really needed by Indonesian people. And then the next point is BMKG has many programs to educate people such as SLG and BGTS. SLG focuses on stakeholders, and then BGTS focuses on students. And the last point is BMKG also publishes many education books. So I think maybe all of you are really curious, right, how to get those books. And if you are really curious, maybe you can ask the presenter how to get it. Oke, jadi coba saya translate ya Pak, Bapak Ibu, saya coba sampaikan dalam bahasa Indonesia. Jadi BMKG memiliki banyak instrumen untuk mendiseminasikan informasi gempa bumi dan tsunami melalui WRSNG, Sirena Tsunami, aplikasi info BMKG dan sebagainya. Jadi aplikasi info BMKG sendiri, fun fact-nya yaitu merupakan aplikasi yang banyak di-download, yang paling banyak di-download, yaitu sekitar 5 juta kali di-download jika dibandingkan dengan aplikasi yang dimiliki oleh institusi Indonesia lainnya. Jadi hal ini menunjukkan bahwa aplikasi ini sangat diperlukan oleh banyak pihak seperti itu. Lalu yang kedua, BMKG memiliki banyak program untuk mengedukasi masyarakat seperti halnya SLG dan BGTS. Jadi kalau SLG tadi itu fokusnya ke stakeholder, lalu BGTS fokusnya ke murid-murid, ke siswa-siswa seperti itu. Lalu yang terakhir, BMKG mempublikasikan banyak buku edukasi, dan apabila Bapak Ibu tadi penasaran bagaimana sih cara dapatnya, nah nanti bisa ditanyakan ke presenter seperti itu. Okay, we have to move to the next speakers. Okay, here we have Dr. Pepen Supendi. He is head of Earthquake and Tsunami Catalog. He completed his doctoral program at Geophysics Engineering at Institut Teknologi Bandung (ITB). Lalu then he has many experience for working. The latest experience was postdoctoral research fellow in Cambridge University. He has many publications. If we search his publication is more than 100 publications. That is really many. And three latest his publications are evidence of multiple subduction slabs beneath Sulawesi from teleseismic P-wave tomography. And then the second one is evidence of magma reservoirs beneath volcanoes in northern Sulawesi and the Moluccas from regional earthquake tomography and seismic structure and volcanism beneath the Sunda Strait from travel time tomography. So maybe for the fun fact again, if BMKG has, for example, like leaderboard for the publication, and Dr. Spendi, he is at the top leader, yeah, okay, with his more than 100 publications. So I would like to invite Dr. Pepen Supendi. Hello, Dr. Pepen Supendi.
Yeah. Hi.
Okay. Can you share the screen?
Sure. Oh.
Okay. Okay, okay, I can see it. Okay, you have 10 minutes for your presentation time. Please, time is yours.
Right. Good morning, everyone. Today, I would like to talk about seismogenic behavior of terrestrial faults near subduction zones. So, here are the generators of destructive earthquakes, including subduction zones, in particular Megathrust and active terrestrial faults. Both Megathrust and active terrestrial faults can cause widespread destruction, fatalities, and economic losses. However, in places like Indonesia, it's more on investigating Megathrust rather than active terrestrial faults, partly as consequence the previous large tsunami events like 2004 Sumatra earthquake. Interestingly, in 2004, Noto earthquake in Japan was in a backup and quite a lot of destruction. This goes to show that even Japan was not all prepared for an earthquake like this. In the bottom right figure, you can see here several active faults places near Jakarta. If this fault rupture, it would threaten for a megacity with over 10 million people. And I think this is one of several reasons why the Indonesian government decided to move the capital city into East Kalimantan. As you know, Indonesia has one of the highest seismic hazard of any country in the world. The highly complex tectonic settings in this region resulting from the collision of the Indo-Australian and Sunda blocks and the direction of the Pacific and Philippine sea plates. In the last 6 years, there has been a huge number of earthquakes that has occurred in Indonesia, including the 2004 Sumatra earthquake. Until 2017, the National Center for Earthquake Studies of Indonesia, NISGEN, has recognized 13 megathrust segments from Sumatra, South Java, Bali, Nusa Tenggara, North Sulawesi and Molucca, and North Papua. And Indonesia has 295 active faults. And I think this number will be increased this year. It's because we have more study about active faults, not only from seismology, but also from a geodesy and geology approach. Fortunately, the additional seismic stations operated by BMKG, in particular in the past 5 years, has greatly improved the detection of small earthquakes from previously unidentified faults. So here are several destructive earthquakes in the last 5 years, including Mamuju Majene in West Sulawesi, Semangkobay earthquake sequence in southern Sumatra, Floresi earthquake in North Nusa Tenggara, Pasaman earthquake in West Sumatra, Cianjur earthquake in West Java, and Jayapura earthquake sequence in Papua. First of all, I would like to talk about Mamuju Majene earthquake. So, this earthquake occurred on 14 December 2021 with magnitude 6.2 and was preceded by magnitude 5.9 fault blocks. And you can see here in the right figure, the main shock followed by quite small numbers of aftershocks. It's quite interesting. And based on a shock map reported by BMKG, this earthquake produced strong motion up to 6 on the MMI scale in West Sulawesi, caused severe damage to more than 279 houses, and resulted in 84 fatalities. The geological map shows that the damaged areas are located in quaternary sediments, which likely explain the increased ground motion to the region. Based on our result, this earthquake occurred on faults within the Majene fault and thrust belt. The next is the 2021 Semangkobay earthquake sequence. This earthquake occurred in southernmost Sumatra, in particular beneath Semangkobay, starting from 30th June 2021. And based on our results, this earthquake caused by several undetected faults rather than single fault line, and that have similar strike to the West Semangkobay fault. And this fault, part of small graben system, which was likely activated by ongoing extension in the Sunda Strait. The next is Floresi earthquake. This earthquake occurred on 14 December 2021. And the tectonic setting in this region actually is very interesting, because here are the transition zone from subduction to collision, And you can see here in the left figure, several active faults occurs in between of the islands, including Flores Megathrust. Interestingly, based on the seismicity data during this period, there have not been any shallow earthquake with magnitude more than 7.0 in this region. And based on our results, this earthquake occurred on previously unidentified faults, then we call as the Kawatoa fault system, and divided into 3 segments. And local mechanism solutions reveal strike faults. The next is Pasaman earthquake. This earthquake occurred on 25th February 2022 with magnitude 6.1, and based on a shake map reported by BMKG, this earthquake produced a strong motion up to 6 on the MMS scale in Pasaman region. It was also measured at 2 on the MMS scale in nearby Malaysia. And this earthquake was damaged more than 1,700 houses and caused at least 18 fatalities in West Sumatra. And about 6,000 people were evacuated after main shock. Based on the seismicity data during this period, there have not been any shallow earthquake with magnitudes more than 6.0 in this region. However, there have been 4 magnitudes more than 6.0 in the neighborhood of Pasaman, including magnitude 6.1 in 1977, the Doblat earthquake in 2007, magnitude 6.4, which resulted in more than 70 casualties, and the magnitude 7.6 in Translate Padang earthquake, which resulted in 1,100 casualties. Our results show that this earthquake caused by a newly unidentified fault, then we call as the Kajai fault. And focal mechanism solution appears to fault, which strikes parallel to the Great Sumatran fault system. Based on the column static stress chance, the main shock increased straight to the north, east, south, and west. And to the north and east, there are high column static stress chance that are unaccompanied by any aftershocks, which might increase the likelihood of aftershock, large earthquake on the Angkola and Sumber faults. The next is Cianjur earthquake. So this earthquake occurred on 21st November 2022 with magnitude 5.6. Unbelievable, this earthquake will damage more than 40,000 houses and caused at least 321 fatalities in Cianjur, and economic losses up to 4 trillion Indonesian rupiah, or equals to $257 million US. Actually, the Cianjur area covered by young volcanic deposits from surrounding volcanoes, including Mount Gede, and traversed by Cimandiri Fault with total length about 100 kilometers and divided into 3 segments, including Cimandiri Fault, Nyalindung Cibubur Fault, and Raja Mandala Fault. While the behavior of this fault is well understood, the Cianjur earthquake was not located along any of its recognized segments. Based on the seismicity data during this period, there have not been any shallow earthquake with magnitudes more than 5.0 in this region. However, based on intensity observations during this period, the Cianjur area has experienced events of magnitudes 7 to 8 on the EMS 98 in 1834 and 1879. However, due to limited station coverage during that period, the source fault of both earthquakes could not be meaningfully constrained. So this is initial location. We detected and located 283 events, consist of 3 foreshocks, main shocks, and 279 aftershocks. Based on the pattern of reliculated hypocenters, we suggest this earthquake caused by conjugate pair of faults trending north-northwest, south-southwest, and west-southwest to east-northeast. Local mechanism solutions reveal strike faults with nodal planes oriented in the same direction of the pattern of relocated hypocenters. And several agencies tried to interpret these faults with different direction. For instance, BMKG, they interpret this fault trending northwest to southeast, the Geological Agency trending southwest to northeast, and so on. Fortunately, our results accommodate their interpretation. Based on the column static stress chance, the main shock increased stress to the north-northwest and west-southwest, which coincides with the distribution of aftershocks in this area. And the Cianjur earthquake has also generated high column static stress chance to the south-southeast, which might have implications for the likelihood of large earthquakes occurring on the Rajambaral fault. Unfortunately, this fault is very close to manifestation centers. Even a moderate earthquake along this fault might pose significant hazard to the region. The last is the Jayapura earthquake sequence. This earthquake occurred in North Jayapura, Papua, starting from 1st January 2023. Even though this area surrounded by this fault, our focal mechanism solutions appears normal fault. This is my last slide. Several recent destructive earthquakes in Indonesia serve as a reminder that shallow cluster earthquakes caused by active terrestrial faults, in particular located near large population centers, pose a major natural hazards. Mapping these active faults is very important for updating seismic hazard maps and understanding their implications. However, without any implementation and law enforcement or building codes, the seismic hazard maps are nothing. Thank you.
Okay, thank you very much, Dr. Pepen Sudvendi, for your presentations. I think we have learned a lot of information from his presentations, and I have summarized some of them. Let me explain. The first is Indonesia has many earthquakes that always occur, and one of the reasons to move Indonesian capital city because of the present capital city is prone to earthquake. And then the second one is even small earthquake like Mamuju earthquake can cause large destruction because of how to say the site locations, how we call it, or sand type. The type of the sand in that location is soft or hard. For the soft soil, it can trigger high destruction, even though the earthquake is small. And the last is Dr. Supendi and his team has successfully found many faults, such as Krakatoa fault in North Nusa Tenggara Barat and Kajai fault in Sumatra Barat, if I'm not wrong. And that information was really important for local government to build their city. Okay, I think that's all from the third presenter. So we move to the last presenter. We have our important guest from Kobe University. We have Prof. Soichi Yoshioka. He is head of the Research Center for Urban Safety and Security, Graduate School of Science from Kobe University. Okay, he graduated his doctoral degree at the Department of Geophysics, Graduate School of Science in Kyoto University. He had some experience for working. The latest is director of the Urban Safety Research Center, Graduate School of Science in April 2020 until March 2020. And from the October 2009 until present, he is a full professor in Research Center for Urban Safety and Security, Kobe University. He had published many publications, and the last of his publications was Subduction Thermal State, Metamorphosis, and Seismicity in the Makran Zone in 2025. So, Professor Soichi Yoshioka, can you share your screen? Okay. Okay, I can. Okay. I still cannot see your presentation, Professor. Reset screen maybe. Okay, I can see it. Okay, Professor Soichi Yoshioka, you have 1 hour for your presentation time, and you can start to present by now, please.
Okay. Thank you for your introductions. It is my great honor to give an opportunity to present my PhD research. The title of my presentation is here. It's a very lengthy. The temperature and dehydration fields estimated from 3-dimensional thermomechanical modeling in subduction zones and their possible relationship to interseismic events and volcanic chains. And here, this is we're at the Southern Pacific region, and in our previous research, we performed the 3-dimensional thermomechanical modeling in these regions. So that this brown colored region is a region where the subduction zones, where the analysis of the thermomechanical modeling have been already done here. And these red region is the 5 subduction zones, such as Alaska, southern Chile, Java, and Costa Rica, and the Aleutians will be investigated in our nationwide ongoing big project, Science of Slow to First Earthquakes. And then today, I'd like to focus on the recent research of the southern Chile and the Java. And my presentation consists of 4 parts. The part 1, case study in the southern Chile subduction zone, and part 2, case study near the Chile triple junction, and part 3, the preliminary study in the Java subduction zone. And if we have time, I'd like to give a short presentation on the 1995 Great Hanshin-Awaji earthquake, which occurred in Kobe. And then the first topic is this one, the case study in the southern Chile subduction zone. And this is a more detailed title of my presentation, the 3-dimensional thermal structure and dehydration in the southern Chile subduction zone and the relation to the interplate earthquakes and volcanic chain. And this research has been done in collaboration with the researchers in the University of Chile. And this is the research background, but I'm sorry, some of them are written in Japanese. And here, this is the subduction zone. The oceanic plate is subducting. It is a continental plate here. And then here, maybe I think the Megathrust earthquakes, there is a research that the Megathrust earthquake are strongly related to the temperature range of about 150 to 350 degrees or something like that. The up dip and the down dip side of this Megathrust earthquake region, the slow earthquakes occur in many areas, such as Alaska and Japan and Chile and Taiwan or some other areas. So maybe this slow earthquake is strongly related to the occurrence of this Megathrust earthquake. And in the deeper portion, maybe in association with subduction, dehydration of the hydrous minerals takes place because in the deeper portion, the temperature is high and the pressure is high here. And then maybe it produces magma and then causes volcanic chain or something like that. This is the major scenario. And then, so here, the first topic is in the southern Chile subduction zone. This is a technical setting in the southern Chile subduction zone. But here, this is the location of the target region. Here, this is the enlarged map in this region. So that in this region, the here seafloor age is relatively young here because the here near here, the southern part of this region, the Chile Beach is subducting. So that toward the south, the age is gradually decreasing. So it becomes younger toward the south. And also the here, this black contour line represent the slab surface geography, the subducting Nazca Plate. And the contour interval is 20 kilometers, which is taken from the Hayes et al. 2018. That is the so-called slab 2 model. And then this orange colored contour and the red colored contour represent the seismic slip of the 2010 Maui earthquake, whose magnitude was moment magnitude was 8.8. And this one is the seismic slip of the 1960 Valdivia earthquake, which is the largest megathrust earthquake, which was recorded by the instrument in the world. The moment magnitude was 9.5 here, like this. And also the here, this one, triangle, red triangle indicate a volcanic chain called the Southern Volcanic Zone. And this is the current convergence rate here. The Nazca Plate is subducting beneath the continental South American plate. And then the convergence rate is about 6.2 centimeters per year along the trench toward the northeast direction. This. And this is the Hope et al. Research. So that they obtained the slip distribution of this Valdivia earthquake, 1960 Valdivia earthquake. So that they use the tsunami waveform data here in the Southern Pacific region, and also they use the leveling data comparing the before and after this megathrust earthquake. And then they use a joint inversion and obtain the slip distribution, seismic slip distribution like this. And then the objective of this study is to construct a three-dimensional thermomechanical model associated with subduction of the Nazca Plate and estimate the thermal state for to interpret megathrust earthquakes, and to calculate water content and dehydration gradient by using phase diagrams of hydrous minerals in the slab, and discuss the relationship to the volcanic chain. And this is a follow-up study of Iwamoto et al., which was published in Geoscience Letters in 2024, and we update the results. And this is the observed data to constrain the thermal structure. These are the global heat flow database. This database is updated every year. So the global heat flow database. And the heat flow is can be calculated by this equation. It's a very simple one. The K is the thermal conductivity, and T is the temperature, and Z is the depth. So that this one is a so-called temperature gradient depth direction, and multiplied by this thermal conductivity. And we can obtain the heat flow. This is an observed one, and also we can also calculate this one from our thermal model. And we can compare our model and then the observed one to constrain our thermal structure model. And this is the data in the southern Chile subduction zone. Here, heat flow data. The color shows the heat flow. The warm color indicates the high value heat flow data like this. And here in this region, we have 105 points from which are taken from the global heat flow database. And then we can compare the observed heat flow data like this and the calculated heat flow data. And then we obtain the root mean square, and then we take the residual. And then there are several pre-parameter, and then the minimizing this value be the optimal model. So that in our study, the pre-parameters are as follows: effective friction coefficient, like this, the plate interface, and with or without a rigid mantle wedge. And then I'll explain this one in the next slide. The first one is this one. And this method is a governing equation. We use the so-called fluid material here, and then we use an elastic approximation, and we use the improved source code by G and Yoshioka of the Stack 3D, which was originally developed by Takuei and Z 2003. And we use the three equations: conservation of mass and the momentum and the energy, like this. And then we solve these equations as a time marching problem. And here in this energy equation, we consider some heat sources such as viscous dissipation, adiabatic compression, and radioactive heating and frictional heating. And this one is very important, which includes the effective friction coefficient mu prime, like this. And here we use the viscosity eta here. Viscosity eta is given as the composite viscosity of diffusion creep and dislocation creep using the formula proposed by Barkett and Pillion in 2010, like this. And then this one is the QF, the frictional heating of the plate interface. And this one can be explained by this one. This one, the shear stress at the brittle one, and this is the ductile one, shear stress, like this, multiplied by this strain rate, like this. So this one, mu prime, the effective friction coefficient, can be obtained like this. This is the brittle shear stress, and this is normal stress, and then this coefficient is the effective friction coefficient. We change this one as a free parameter, like this. And then for this one is the ductile region. Then we can obtain the shear stress using this one for the ductile ratio, this which is taken from Karistan to 1982. And for the rigid mantle wedge, here this is the result is a rigid mantle wedge. As for the rigid mantle wedge, some according to Wada and One, which performed two-dimensional thermal modeling, they proposed that there is a high serpentinized region here, that is the corner of the mantle wedge. So here this part may be a little bit cold, that is because the flow is stagnant, and that is so they proposed like something like this. So we also post that the possible existence of this triangular region, which is called rigid mantle wedge, like this. And then here this is a model setting. So here this region is a model region, the blue dotted box. And the model region is set to include a source region of the 1960 Valdivia earthquake and the 2010 Maui earthquake, and also the southern volcanic zone, this one, like this. And the model size is 450 kilometer in the perpendicular to the trench axis, and 1200 kilometer in the along arc direction, and 200 kilometer in the depth. And here this is the boundary conditions for the parallel piped three-dimensional model, like this. So that this is the boundary condition shown here. There are two kinds of boundary condition, temperature and flow. On the top of the model, the temperature is fixed to be 0 degrees, and then the velocity, the flow velocity is 0 here. And then for these side boundaries, for side boundaries and the bottom boundaries, the permeable condition and the adiabatic temperature condition is assumed here. And for this boundary, where the oceanic plate is subducting, we consider the permeable condition, but also the temperature condition. We did so-called fixed temperature as a function of depth and the seafloor range. So based on the McKenzie in 1967, this is so-called plate cooling model, something like that. So that maybe this one
You are muted, Professor.
this time. So that we change spatial temporal change in
Hello?
boundary
We
condition,
cannot
temperature
hear you.
boundary condition here. The initial temperature condition is said to be like this. We use the half space cooling model like this. So using the error function like this
Still
at
muted. Sorry,
a certain
committee.
at the depth shallower than this specific depth. Then we use this one. In the deeper portion, we consider so-called adiabatic compression like this. So here the model setting, and then initially we consider the stratified model. So that consists of the upper crust and the lower crust with the thickness of 0 to 60 kilometer. The upper crust and the lower crust is 16 to 32 kilometer, and the mantle is 32 to 200 kilometer. Like this, and then this crust is assumed to be the thermal conductive layers, and this part, the mantle, is a thermal convection region. And then here, in this region, we consider subduction of the oceanic plate, and then which was realized by pouring the slab material into the prescribed guide here, and then the slab geometry is taken from slab 2 model, as I mentioned before, and the thickness of the slab is a function is given as a function of oceanic plate age by Talcott and Schubert 2002, and the calculation time is to 20 MA to the present. So that is a long time subduction performance like this. So here we consider the subduction history for such a long time, for 20 million years. So this one is the case of the Philippine Sea, near the Philippine Sea plate, near the located in the south of the Japanese islands. So the black solid line here, this is the continental block, and then the colored contour line, the ice crown of oceanic plate, and the white solid line, this part is the spreading center, something like that. And then this color shows the seafloor age, like this. And we consider this one in our model. So this is the subduction history concerning such subduction history, like this. So we divide the 20 million years every 5 million years, and then change the convergence rate and the azimuth like this. And then this is the results, and we can compare our obtained thermal structure with the using the so-called the heat flow data. And then this is the comparison between the observed and the calculated heat flow. The background color indicates the calculated heat flow, and this square, the colored square, show the observed heat flow data, as I mentioned before. And I took some cross section. So this is 6 cross sections like this, and also the across arc direction, and also the along arc direction here. And then this is the observed one, observed heat flow data, and then this is the solid line or dashed line with the calculated heat flow data, and then we determine the optimal model using the evaluation of the root mean square value. And then as a result, we obtain that the black curve is the best fit solution like this. So that in that case, the mu prime friction coefficient, effective friction coefficient is 0.0025, and without rigid mantle wedge is an optimal model. So like this, so that we also consider the case of this rigid mantle wedge here to a depth of about 80 kilometers, but without rigid mantle wedge model is suitable for optimal model in our study. And then this is the simulation, our result. That's animation. I showed animation from 20 MA to the present. The color indicates the temperature, like this, the subducting, like this, from 20 MA to the present, like this. So we obtain the temperature at the present, and then we compare the heat flow data here, like this. And then as a result, we compare the slip distribution of the Megathrust earthquake, which occurred in this region. So the first one is here, 2010 Maure earthquake, whose moment magnitude was 8.8 here, this one. And then the precise slip, if we take precise slip larger than 5 meters, then the up dip, the temperature here, up dip temperature would be about 200 degrees. And also the down dip temperature here would be 380 degrees, something like that. And on the other hand, 1960 Valdivia earthquake with magnitude was, moment magnitude was 9.5, here, this one. And the upper dip limit, there's no temperature, because this one break reach the Earth's surface. So there's no temperature, the upper dip side. And on the other hand, the down dip side temperature would be almost 500 degrees, something like that. And then this is the schematic figure obtained, proposed by Hindman et al. 1997. And then they proposed that the Megathrust earthquake occurred at the temperature ranging from 100 to 150 degrees to 350 degrees. So generally the locked zone, and then all of a sudden the breakage takes place. The Megathrust earthquake takes place at this temperature range. And in the deeper region, from 350 degrees to 450 degrees, called the transition zone, like this. And then if we compare this schematic model with our result, maybe in the case of the 2010 Maui earthquake, whose magnitude was 8.8, maybe that this one is more or less consistent with this locked zone, consistent with previous study. On the other hand, 1960 Valdivia earthquake, so the upper dip limit, there's no data, but the down dip limit is about 500 degrees, which is deeper than this transition zone, like this. So this one's not consistent with the previous research, and then I think there are two reasons for this. And the one reason is that the subducting oceanic plate is very young, as I mentioned previously. And then the second reason is this is sufficiently large moment magnitude. So this length is very large, and also the width is very large, because this is the largest moment magnitude earthquake which occurred in the world. Okay. Okay, fine.
10 minutes left. You can continue.
Okay, thank you. And this is the calculating the water content from the summer structure. So we divide the slab into the three layers. The top layer is the oceanic sedimentary layer with a thickness of about 2 kilometers. Here, this blue color region. And then below that region from 2 to 7 kilometer, the oceanic crust. And then below that one, the 7 kilometer from the top. And then there's respectively, they consist of the turbidite and the mob and the ultramafic here. And then this is the phase diagram of turbidite, mob and ultramafic rock corresponding to the oceanic sedimentary layer and the oceanic crust and the slab mantle respectively. And this is the phase diagram, and then this the horizontal axis shows the temperature. Vertical axis shows the depth here. And then this is the result that I showed previously, that the subsurface temperature. And then if we obtain this subsurface temperature, we know the temperature and the location for the depth. Then we can obtain the what kind of material exists here. This is a water content distribution, and so the blue color shows a higher water content, and the red color shows lower content. Water content. So in general, if the temperature increase or the depth increase, the dehydration takes place like this, and then water is dehydrated from the slab, especially when the color change, and the dehydration takes place sharply like this. And then so this temperature distribution, and this is the phase diagram. And then if we combine this one, we can obtain the water content distribution on the slab surface like this. And then after that, we can also obtain the thermal gradient, the dehydration gradient. The dehydration gradient is a difference in the water content per unit length along the subduction direction like this. So that, for example, here we can find the change of the color. So it means that the dehydration takes place here, and then we can find this color change here, so that we can easily identify the location where the dehydration takes place like this. If we plot this dehydration gradient distribution like this. And then this is the water content distribution like this. This is 0 kilometer, means that the slab surface, and 4 kilometer from the top of the slab surface into the slab, and this is 9 kilometer. So that these ones are corresponding to the phase diagram, or taken from the phase diagram of sedimentary layer, so oceanic crust, and this is the slab mantle, the deeper portion. Like this, and this is the vertical cross section for these two profiles. So this is the slab, and then this part is the young plate, so that the thickness of the slab is thinner compared to this part. And then here we can find the water exists inside the slab, like this here. And then this is the dehydration gradient distribution, like this. So here, if we compare this one with the volcanic chain, then we can find a good agreement between this location of the volcanic chain and the large dehydration gradient here, which is beneficial to identify effective dehydration locations like this. And then this one, the dehydration gradient distribution in the vertical cross section. And then here, the blue colored region shows the high dehydration gradient. And then interestingly, this is the vertical sum of the dehydration gradient at each location. And then interestingly, the vertical sum of dehydration gradient inside the slab, just below the volcano. Volcanic chain is relatively large along the two profiles like this. So this indicates that the fluid in the slab is released at the depth of approximately 100 to 120 kilometers, rises to shallower depths, and decrease the melting point to produce the magma, resulting in the formation of volcanic chain just above it. So in conclusion, for the first part of my presentation, we constructed a three-dimensional some mechanical model associated with subduction, the Nazca plate in the southern Chile subduction zone. And then we estimated effective friction coefficient, mu prime is equal to 0.0025, is very small. This indicates that the subduction hold is very weak. And secondly, the up dip and down dip limits of temperatures of ruptured areas of the two Megathrust earthquakes, the 2010 Maui earthquake, up dip and down dip temperatures be about 200 and 380 degrees respectively. And in the case of the 1960 Valdivia earthquake, down dip temperature would be about 500 degrees. This is a high temperature at the down dip limit. And there are two reasons for this. Maybe the subducting oceanic plate is young and sufficiently large moment magnitude. And then thirdly and finally, the fluids are released from the slab at depths of approximately 100 to 120 kilometers and rise to the mantle edge and decrease the melting point and sufficient magma production to form volcanoes. And then maybe we are running out of time, so then Dr. Wen requested me to give this definitely. So I skip this second part. I'm sorry about that. So almost the similar approach, but we consider the two subduction like this, simultaneous subduction and Antarctic plate and the Nazca plate is different subduction velocity, and also the Chile triple junction is moving northward. Yeah, something like this. And then, but I skip this one, and then the part 3, maybe the preliminary study in the Java subduction zone. Okay, the three-dimensional thermomechanical modeling in the Java subduction zone. So here the technical mapping, maybe you are familiar with this area, so there's no, I don't have to explain the detail, but here the volcanic chain is located here, and this black line is here. The isodepth contours of the slab surface. This is again use the slab 2 model by Hayes et al. 2018, and this is the epicenter of earthquakes. But we just pick up a recent event with moment magnitude 7. So here the west side, Java west side, and the east side, the west one is moment magnitude 7.7. which occurred the July 17, 2006, and then the east one is moment magnitude 7.8, which occurred in June 2nd, 1994. Here, that is the offshore region, maybe the Megathrust earthquake, but it's not the magnitude is less than 8. And this solid color indicates the epicenter of earthquakes of moment magnitude 5 to 7. Here, there are many earthquakes, which are taken from USGS data catalog for about the past 40 years. Yeah, this period 1983 to 2023. Here, like this. And then here, this one is the seismic slip distributions obtained by Bilic and Engdahl 2017 for these two earthquakes like this. And then here this is observed data to constrain the thermal structure. Here this one, I showed this one already, but we also use the interpolated global heat flow model by Lucaso 2019 here. It's the red color indicates high heat flow, and the blue color shows indicate low heat flow. And then the advantage using this data is at the high resolution, spatial resolution, the 30-minute arc, like this, the global. But this one is, as you can see, there are no many regions, no data or something like that, and the high data, but this is a equidistance data like this. And here the heat flow data in Indonesia, the Java. So here this is observed one. Observed heat flow data. This is a color shows the heat flow value. Like this is the northern part here, the west part. This is the east side. The northern part of the island, we can find some data. But in this model region, there are no heat flow data. Here, that's a big problem to constrain the thermal structure. So as I mentioned before, here we use the interpolated heat flow data. Like this is every 30-minute arc, like this. So here, and then we use this data to constrain our thermal model. And then the equation, governing equation is almost the same. So I skip this slide. And this also almost the same. And then the model size is like this. The width is 300 kilometer, and the depth is 450 kilometer. And then no, not this. This is not the depth. This depth is 200 kilometer, and this is the length in the perpendicular to the trench axis, like this. And then so we skip this one, and this is also the same. And then this is the model setting, the boundary condition, like this. This is the trench and the subducting direction. This is the northward. This is the southward direction. And then I also skip this boundary explanation of this boundary condition. And this is again the same approach. And this is also the subduction history. Every we change the convergence rate and the azimuth. And this is the result of the obtained heat flow data. So that this is the west side and this is the east side. And then this background color indicates the captured surf heat flow data. And this colored circle indicates the observed or interpolated heat flow data. So the triangle shows the observed one, and this circle shows the interpreted data, like this. And this is the comparison for the 6 profiles. So this is across arc direction. These three profiles we took, like this. And then this is along arc direction here, like this. So when we look at this across arc direction, if we change the so-called free parameter of friction, effective friction coefficient, then if the effective friction coefficient is large, of course the heat flow becomes larger. And then if we compare this observation, maybe the most suitable value would be this one. The prime would be 0.002. Like this, the orange colored one would be the best model to explain the observed heat flow data, like this. And on the other hand, the east side, maybe the best one would be this color, green colored one, green colored line, like this. So that in this case, the effective heat flow data, effective friction coefficient is 0.0015. This, and then this is the result, the temperature distribution on the plate interface. But this is still preliminary result. This is the temperature on the plate interface, and this is 350 degrees and 450 degrees, as I mentioned before. And this is the west side, and this is the east side, and this is the seismic distribution obtained by Philip and Engdahl 2007 for these two Megathrust earthquake. So as you can see, look at the distribution of 1 meter, then the slip occurred shallower than depths shallower than the temperature of 350 degrees or 450 degrees. Yeah, so which is consistent with the previous research. Yeah, like this. And also we attempt to obtain the water content using this phase diagram, as I mentioned before. And also this one is a water content distribution like this. So then try to compare our result. This is some temperature gradient, and then we try to compare our result with the location of the volcanic chain, something like that. So this is still preliminary. The conclusion, we attempted to construct a three-dimensional thermomechanical model and estimate separation, spatial distribution of temperature, water content, and the dehydration gradient. The effective friction coefficient for the east and west sides were estimated to be 0.015 and 0.020 respectively, which were small but comparable values estimated in previous studies. And for seismic slip distributions of the two megathrust earthquakes occurred in the temperatures ranging from 100 to 350 degrees or up to 450 degrees, which are consistent with previous studies. So finally, I'd like to show videos. It's okay if I show videos with a sound. Sound. Yeah. So I just change the sound. Sound. Okay. No, it's okay. Share screen. Share screen. Yeah, share screen. Okay. Let's try. Okay. Right. Oh, there's no sound. Yeah. This is session. Please share. Sorry.
Stop share.
Stop, no?
Yeah.
Stop share. Again. Okay. Yeah. In 2022, Kobe University started an international project with research partners in Mexico and Chile to clarify the mechanism behind huge earthquakes that will occur in the three countries. Ever since the 1995 Great Hanshin-Awaji earthquake hit Kobe and the surrounding area, Kobe University In 2022, Kobe University started an international project with research partners in Mexico and Chile to clarify the mechanism behind huge earthquakes that will occur in the three countries. Ever since the 1995 Great Hanshin-Awaji earthquake hit Kobe and the surrounding area, in 2022, Kobe University started an international project with research partners in Mexico and Chile to clarify the mechanism behind huge earthquakes that will occur in the three countries. Ever since the 1995 Great Hanshin-Awaji earthquake hit Kobe and the surrounding area, Kobe University has been conducting comprehensive research in earthquakes and disaster prevention. Slow earthquakes are slow slip phenomena that occur at plate boundaries near seismic gaps, indicating a possible relationship between huge earthquakes and slow earthquakes. Through computerized data analysis and numerical simulations of slow earthquakes, our research seeks to elucidate the mechanisms by which huge earthquakes occur. For this purpose, we use two different approaches. One is spatial-temporal slip distribution associated with a slow slip event on a plate boundary inverted from GNSS data. In this video, the arrows denote the degree and direction of slippage, and red gradient indicates the area that experienced significant slippage. We can gain understanding of past underground slip events using GNSS data obtained from the surface. The other approach that we use is three-dimensional thermomechanical modeling. We constructed a three-dimensional thermomechanical numerical model for the subduction of an oceanic plate by numerically solving equations of conservations of mass, momentum, and energy. This video shows simulated time evolution of three-dimensional temperature and flow fields in Alaska subduction zone spanning 18 million years ago to the present. Red and blue colors denote high and low temperature areas respectively. Colored arrows represent flow fields in the mantle. The temperature influences the friction properties at the plate boundary. These computations were carried out using a high-performance computing system in our lab. We pursue highly original research. Our research originates from ideas that are born from our own thinking or from discussions with research collaborators and students. Our team consists of researchers with interdisciplinary and international backgrounds. We study huge earthquakes in order to save human lives. We welcome researchers and students to our project. This is a promotion video. Thank you for your attention. And then I'd like to take 10 minutes. Is okay? Okay, then I change the slide.
Yeah, it's okay.
Change the slides. I'm sorry. It's about Okay, then let me briefly introduce what happened at the time of the 1995 Hyogo-ken number earthquake. Moment magnitude was 6.9. The other name is the Great Hanshin Awaji earthquake. So this video is okay.
Yeah, have you set your song? Maybe please share again.
Share again.
Yeah, share again. Share screen again. Okay, it's okay.
Okay, it's okay.
Slideshow.
Slideshow. Okay, this is the video.
1995年に起きた兵庫県南部地震。この地震の震源と震源地はこの中にありました。大陸プレート内部で発生する地震は建物を直接破壊してしまう危険性があります。
The earthquake which occurred in inland earthquake, so the active force. So move like this. Continuous, not. This is the active force like this. And then again another big one. What's most
観測史上初となる震度7という大きな揺れを記録した阪神・淡路大震災。634人もの尊い命が奪われました。そのほとんどが倒壊した住宅や建物の下敷きになったことによる圧死でした。普段住み慣れた我が家が一瞬にして凶器に変わったのです。地震後に発生した火災は200件以上。何度電話しても消防につながらなかったり、建物の倒壊によって道が塞がれ、消防車が通行できなかったといったことがありました。
Many buildings that collapsed, the shortage of water or something like that, and then it's just like the war after the war, bombardment like this. Yeah. I want to skip this one. Okay, then. Okay. So in Japan, the seismic intensity is categorized into the 10 scale like this, which was defined by the Japan Meteorological Agency. So the 0 to the 7. Here the 5 lower and the 5 upper and the 6 lower and the 6 upper like this. At the time of the Kobe earthquake, we recorded the the maximum intensity, seismic intensity of 7 here. So in this case, you can see the collapse of the building takes place like this. And then here, this is the Kobe city, and we can find this orange colored region. This is called the so-called, how do you say, the damage area. The reason is seismic intensity of 7 or something like that. So, and then the fire took place near here, and then the trains are inclined like this, and as I showed the video here, the highway collapse like this, and then this one the drop, and then this driver stopped just before this one. Yeah, this, and then this one the famous picture, the collapsed Hanshin expressway, and then and 1 year ago, just 1 year ago, North Ridge earthquake occurred here, the 1994, January 17. And then at that time, in California, the magnitude was 6.7, and the epicenter was 15 kilometers deep, and the 57 people were killed, and approximately 5,400 were injured. And then at that time, the Japanese researchers who were involved in the construction said that these things, the United States, never happened in Japan. But in 1 year, ironically, the same thing happened in Japan, in Kobe. So this is the fault trace like this, the Awaji Island. And then as you can see that this part is uplifted compared to this one. And then the right lateral motion took place. And here, this is the trace. And then maybe the Nojima fault, the maximum slip occurred near here, Hirabayashi. Maybe more than 1 meter, the sliding, the right lateral and the vertical, both. But this is the picture here. So this position used to be the same. So that this part is uplifted 1.2 meters, and the move right lateral 1.2 meters or something like that here. And then this is also again the video. I'm sure it works well.
亡くなった方を思い出すということで、保存することには反対される方もいましたでしょうか。大体両線が平ら。
東から太平洋プレートとフィリピン海プレートの力が合わさって押し付けます。そして西からはユーラシアプレートの力が働いています。意外な力に挟まれて、淡路島は小島断層以外にも他の断層を作りながら盛り上がってきたんです。そして
Okay, and here this is a typical collapse of the middle floor building. Like this, so the one floor is collapsed completely, like this. So, and then this is the cause of the collapse of the how to say, the middle floor or something like that. And most of the building where mid-story collapse were observed were office buildings with few walls and were designed before 1971. It's believed that the cause was the design shear force of the middle and the upper floors was small under the old standards, and that the strength of the upper floors were relatively insufficient because the structural regulations prevented the structural strength from decreasing. In addition, the cross section of the columns becomes smaller every few floors as you go up, and the structural style changes. So this one is sound boiling due to liquefaction near the coast. And skip this one. And this is the famous liquefaction movie, the Niigata earthquake, which occurred.
地盤が支持力を失う現象で、砂の粒子が多い地盤に特に起きやすいと言われています。新潟市の大部分も信濃川が運んだ堆積物によってできた、そうした地盤だったのです。液状化現象は埋め立て地などへの生活圏の拡大が直面した新たな災害でした。
The top of layer and then so sediments are located here. So this one, the Kobe earthquake, as you can see, there are many second story wooden houses here, and then the first floor is collapsed, and the second floor sort of fell down like this. And this earthquake occurred at the time of 47 or 46 early in the morning. So many people are sleeping in the first floor, and then all of a sudden the second floor collapsed. So then 80% of the people died by the collapse of the building. And then this one is also, as you can see, that the collapse of the building. And as you can see, that this building, this one is okay because this is a concrete building, but this one is an old building that completely collapsed, and this one is not so old, but it's supported by this wooden pole like this. So this is not by the how to say the ground condition, but the building here. So this one is very vulnerable and very weak. This building, so that completely collapsed by the shaking. So we changed the building code like this. Before 1971, the building code is like this, and after that, the 1968, a big earthquake occurred, and they changed the building code, and the second generation building becomes much stronger. And then after that, the 1978 Miyagi earthquake occurred, and this is not enough, so that we changed the building code again. So this building is relatively strong, so the damage, the Kobe earthquake, is also not so strong. But as I mentioned, that there are many wooden houses, old wooden houses. That's a big collapse. That's a big problem. So in 2000, after the 1995 Kobe earthquake, the building code for the wooden houses changed like this. So this I skip this one. So this one the most intense area, the seismic intensity of 7. And there are big debate after the earthquake. So one hypothesis would be here there are hidden fault here. That's the cause of the Kobe earthquake. Another hypothesis is that maybe in Kobe there's a special location located like this here. The ocean. This is the mountain range. So there's some such effect may cause this concentration of the strong intensity or something like that. And now we believe the latter hypothesis. And then so this is the schematic figure. So this is the image of Kobe. So this is the mountain side. This is the ocean side. And then I'm sorry, this is written in Japanese. So this is the soft sedimentary layer like this, and then And here, if we input the seismic wave from the bottom, and then this is the original seismic wave like this, and this is the granite high solid material. And if we observe this one, maybe the almost the same seismic wave can be observed here. But here, in the sedimentary layer, maybe the amplitude becomes larger. And then if we observe this at the top of the very soft layer, this one becomes larger, and then the seismic wave becomes longer, or something like that. So here, this is the image of the Kobe earthquake. From the bottom, the seismic wave comes, and from the mountain side and the oceanic side, here the H wave comes here, from here. This one is faster wave. It comes here, and then it's horizontally moving like this. And on the other hand, from the bottom, this one becomes to the sedimentary layer, and then as a result, the velocity becomes lower, and then the amplitude becomes larger, and also more here the shallow part, the velocity becomes lower, and then the amplitude becomes larger, and then as a result, these two waves interact each other. Then as a result, this region with seismic intensity of 7 took place. That's what we are thinking about. Okay, that's the end of my talk. Yeah, thank you so much.
Okay, thank you very much, Professor Sophie. So let me conclude a little bit because our time is limited. So there are two points: the deeper the layer, the hotter it is, and the less water content it has. And the second one is the Kobe earthquake was one of the most destructive earthquakes in Japanese history. Jadi semakin dalam kedalaman layer, ketika layer menunjang ke bawah, jadi semakin panas layer itu, namun water contentnya itu semakin berkurang, Bapak Ibu. Jadi yang kedua, Kobe earthquake merupakan gempa yang paling dahsyat di histori Jepang seperti itu. Okay, so we move to the next agenda, which is Q&A sessions. So I will give maybe one opportunity for the offline. Anyone want to ask? Okay, please.
Let me introduce myself first. My name is Farhan Rozopiro from Geophysics in BMKG. One question, Professor Suzuka. How do we obtain the inflow data so we can process the data, and what source code did Professor use to process the data? Thank you.
How to obtain heat flow data?
Heat flow.
Heat flow data.
What data that you use?
Heat flow data. Heat flow data. So,
and the code.
yeah, heat flow data. We have a database, the global heat flow database, and then maybe the German researchers collected the heat flow data for the last maybe 50 years. On every year they improve and they collect them, so that we can that data is available from the website.
What website?
Website. Maybe I don't remember exactly, but you can find the global heat flow database. Yeah, global heat flow database. You can find the database, and then you can freely download the data. Yeah, and then every year it's updated. Then the data increases more and more, and then the quality of the data comes increasing because recent data is more high accuracy data. I think so. Yeah. Maybe all data maybe not so reliable, but the recent data may be reliable. Yeah, I think so.
And source code process.
Excuse me.
Source code to process the
source code.
Source code, yes.
Source code to process over the
or
3-dimensional modeling. It's not the open code. We developed by ourselves, so it's not open code. I'm sorry, but if we collaborate with them, so we can share the source code. Yeah, no problem at all. Yeah, but not open for everyone. Yeah, I'm sorry about that.
The big news. Thank you.
Thank you very much.
Okay, online. Okay, so the next is from online. Please. Okay, here, Sensei, maybe you can see the questions out there. Yeah. How do you measure the temperature at those certain zone? I think it's a bit similar with him.
Yeah. So how to measure maybe the heat flow data. We just use the heat flow data so that we obtain the thermal structure and then to so to constrain the thermal structure, we use the observed heat flow data. So then we validate our thermal model. Yeah, something like that.
Okay, thank you. So now we move to the offline participants. Please.
Yeah,
Dr. Daryono.
thank you, Sensei. I have a question regarding the buckling slab. Yeah. Are there any special characteristic of the slab buckling for each subduction zone that you have studied in Japan, Java, Alaska, also Chile? Related to the factor that affect buckling slab, is there any effect of temperature, water content in the slab?
I don't really understand what you mean. Buckling.
Yeah, buckling.
Buckling.
slab.
Buckling.
Yes. The character of the section.
Yeah.
Yes. Yeah. Are there any special characteristic for each zone? Japan, Alaska, Java, Chile.
The same characteristics, except for Java, maybe the large earthquake, Megathrust earthquake occurred, and then the slow earthquake accompanied. Yeah, in Chile and Alaska and Japan. Yeah, so maybe the slow earthquake, maybe the key to understand the generation mechanism of Megathrust earthquake. So now the research is now ongoing, so that we still don't know the relationship between the slow earthquake and the Megathrust earthquake. But I think the slow earthquake may be the important role to cause a Megathrust earthquake. So I'm not sure, but in Java or Sumatra, there might be the slow earthquake. Yeah, if we observe that one.
Yeah.
Yeah. To detect the slow earthquake, maybe we need the GNSS data, high density GNSS data, something like that. Yeah, that's an important thing.
Yeah. One more question. If the hypocenter of the earthquake in the accreted sediment, I mean in the detachment zone, can it be called as Megathrust earthquake? If the hypocenter under this accreted sediment, can we call it as the Megathrust event?
What do you mean? I got
Evolutionary prism, Pak.
Evolutionary prism? Yeah, generally.
For example, in the southern part of Java, we have a slow earthquake in 1994 and 2006.
Yeah.
Yeah. I think this is not the Megathrust. Because the epicenter is under accretionary prism. So we cannot call it as Megathrust earthquake. How about you?
Well, I'm not sure, but generally speaking, it's difficult to consider that in the accretionary prism, the Megathrust earthquake occur because it's very software or something like that. So generally speaking, I think the Megathrust earthquake occur on the plate interface. But sometimes maybe it's the branching takes place. If the earthquake occur here, the hypothesis is propagate upward. And then the branching takes place, and then going into the, I would say, the accretionary prism.
Yeah.
Yeah, and then there are many thrust modes inside the accretionary prism. But that is I think the hypocenter would not be inside the accretionary prism because it's a very soft layer. Yeah, but the branching and the may take place. Yeah, I think so. Yeah, especially in the Nankai subduction zone, Southwest Japan. Yeah.
Okay, please, one more from online, please.
Yeah, one more.
Actually, more.
Online, what's it's too long. What? I cannot see it.
Bacain mo.
Okay, based on the video of the Kobe earthquake,
Yeah.
if I'm not mistaken, would this event be classified as long period ground motion? If correct, I would like to ask the following questions. Long period ground motion generated by large earthquakes can cause resonance in tall structures, such as skyscrapers, suspension bridges, and storage tanks. How do the characteristic of the seismic response spectrum to long period seismic wave influence the earthquake resistant design of high-rise building in region vulnerable to megathrust earthquakes? Are there specific parameters within the response acceleration spectrum that can be used as key indicator to assess the susceptibility of building to long period ground motions? Maybe for the first question, say, would this event be classified as long period ground motion?
Well, it's difficult to say, but maybe at the time of the how to say the 2016 Kumamoto earthquake, maybe the same magnitude. Then maybe the short period ground motion something like that. I showed the video happened, and also at the same time the long period the ground motion takes place. So I mean the high-rise building the moving like this. So I think that the both happen, especially the long period ground motion takes place far away, from the Megathrust earthquake. For example, in the 2011 Tokyo earthquake, the high-rise building in Tokyo or Osaka moved like this for a long time. Maybe the distance is more than 500 kilometers from Tohoku to the Osaka, and then there are many damages or something like that. And so we have to be very careful about such building for high-rise building because the long period seismic wave does not how to say survive for long distance. So and then if there's a resonance, because of the resonance, because maybe the high-rise building is moving for a long time. So maybe we have to change some building method or something like that. So I mean maybe there are some earthquake-proof buildings. So in the bottom of the the building, there are some damper to absorb the shaking or something like that. Or high-rise building or something like that. So that's one way to avoid such long period of shaking for the high-rise building or something like that. I think so.
Okay, maybe we can wait for a moment for the azan. Okay.
Okay.
Okay, thank you for the waiting. So since our time is really limited, so we have to say sorry that we cannot accommodate all of your questions. But don't worry, you still can ask your question through their email, as you see at this share screen. Okay. So this is the end of this session. So we have to move to the next agenda. Please, Ms. Safira, time is yours.
Thank you to Mr. Sidik Hargo for moderating the expert presentation and discussion session in this webinar. Ladies and gentlemen, we're going to the last agenda, which is the closing remarks, which will be delivered by the Director of Earthquake and Tsunami. To Dr. Daryono, SSC MD, time is yours.
Thank you, Mbak Tira. Sensei Yesi, Isilka. I'm so grateful to you that you have visited my office, and I really appreciate you because for your kindness, for your help during my team in Kobe. So my team, to Dr. Weni and team, got some data and valuable lesson learned from Kobe that it can develop my mitigation effort. My name is Daryono, Director of Earthquake and Tsunami of BMKG. Assalamualaikum warahmatullahi wabarakatuh. Ladies and gentlemen, As we come to the end of this insightful webinar on preparedness for Megathrust earthquake, sources, impacts, and mitigation, I would like to express my deepest gratitude to all our esteemed speakers, panelists, and participants. Your contribution have been invaluable in enhancing our understanding of the complexities surrounding Megathrust earthquake. Throughout today's discussion, we have explored the origin and potential impact of this formidable nature event, as well as the mitigation strategies that can help us prepare and respond effectively. The knowledge shared here is not just theoretical, it can practical significant that can save live and protect our communities. A special thank you to Professor Yoshioka for sharing invaluable insight into Megathrust earthquake preparedness, not only in Indonesia, but also in other seismically active regions such as Chile, Alaska, and Japan. Your expertise has greatly enhanced our discussion and preparedness effort. I would also like to extend my sincere appreciation to the organizing team for their dedication in making this webinar success. Your hard work behind the scene has ensured a seamless and productive event, allowing us in focus on this crucial topic. Our commitment to preparedness and resilience is more important than ever. As we move forward, let us continue the collaborate, innovative, and implement the strategies discussed today. By working together, we can build a safer and more resilient in the future. Thank you once again for your participation and dedication to this cause. Let us remain vigilant and proactive in mitigating the risk of Megathrust earthquake. Stay safe and stay prepared. Thank you for your attention.
Thank you to Dr. Daryono, MSE, for your closing remarks. And there are some souvenirs. Professor from Directorate of Earthquake and Tsunami, maybe Professor Soichi Yoshioka. As our gratitude, please accept it. Yes.
Gitu mas, oh gitu mas. Gitu.
Thank you very much, Professor. Oh. Okay, ladies and gentlemen, we have finally completed today's agenda. Me as Master of Ceremony apologize for any mistake in words or deeds in guiding the agenda. I would like to extend our sincere gratitude to all speakers and participants for your time and contributions. Your active participation has made this event a great success. We hope that the knowledge shared today will inspire concrete action in improving earthquake preparedness and mitigation efforts, and let us continue to work together in building a more resilient society. Thank you once again, and we look forward to seeing you in future discussion. Stay safe, stay prepared. Goodbye, and have a wonderful day. Wassalamualaikum warahmatullahi wabarakatuh. Salam.
Warahmatullahi wabarakatuh.
Namo Buddhaya.
Mufti mana Mufti?
Tuh.
Tidak ada obrolan.